Hi, this is Remembering the Past, the show where we talk about people who died recently who've had a profound effect on our history, our society, or our culture. And in our ongoing series on Nobel Prize winners, tonight we're going to talk about Dr. Hans-Georg Dehmelt, who died recently at the age of 94. Dr. Dehmelt won a quarter of the Nobel Prize in Physics in 1989 for his work in ion trapping. He was able to isolate the electron and discover some of its magnetic and electric properties. And in this way, he was able to validate some of the basics of quantum mechanics. He was a nice German boy born in Göring, Germany, which is at the border with Poland, right near the Czech border as well. But he moved to the United States, became an American citizen, and did most of his important work at the University of Washington. Here's a report on the life of Dr. Hans-Georg Dehmelt.
Hans-Georg Dehmelt is a German-born American physicist who was awarded Nobel Prize in Physics in 1989 for co-developing the ion trap technique with Wolfgang Paul, for which they shared one half of the prize. Their technique was used for high-precision measurement of the electron G-factor. At the age of 10, Dehmelt enrolled in the Berlinisches Gymnasium Kloster, a Latin school in Berlin, where he was admitted on a scholarship. After graduating in 1940, he volunteered for service in the German army, which ordered him to attend the University of Breslau to study physics in 1943. After a year of study, he returned to army service and was captured during the Battle of the Bulge. After his release from an American prisoner of war camp in 1946, Dehmelt returned to his study of physics at the University of Göttingen, where he supported himself by repairing and bartering old pre-war radio sets. He completed his master's thesis in 1948 and received his PhD in 1950, both from the University of Göttingen. He was then invited to Duke University as a postdoctoral associate, emigrating in 1952. Dehmelt became an assistant professor at the University of Washington in Seattle in 1955, an associate professor in 1958, and a full professor in 1961. In 1955 he built his first electron impact tube in George Volkoff's laboratory at the University of British Columbia and experimented on paramagnetic resonances in polarized atoms and free electrons. In the 1960s, Dehmelt and his students worked on spectroscopy of hydrogen and helium ions. The electron was finally isolated in 1973 with David Wineland, who continued work on trapped ions at NIST. He created the first germanium atom in 1976, which he then used to measure precise magnetic moments of the electron and positron with R.S. van Dyck into the 1980s, work that led to his Nobel Prize. In 1979, Dehmelt led a team that took the first photo of a single atom. He continued work on ion traps at the University of Washington until his retirement in October 2002. In May 2010, he was honored as one of Washington's Nobel laureates by Crown Princess Victoria of Sweden at a special event in Seattle.
Here is how the Nobel Committee described Dr. Dehmelt's work. The works of Nobel laureates have led to dramatic advances in the field of precision spectroscopy in recent years. Methods have been developed that form the basis for our present definition of time, and these techniques are applied for such disparate purposes as testing Einstein's general theory of relativity and measuring continental drift. An atom has certain fixed energy levels, and transition between these levels can take place by means of emission or absorption of electromagnetic radiation such as light. Transition between closely spaced levels can be induced by means of radio frequency radiation, and this forms the basis for so-called resonance methods. The first method of this kind was introduced by Professor Isidor Rabi, who we've talked about before. He did that in 1937, and the same basic idea underlies the resonance methods developed later. In Rabi's method, a beam of atoms passes through an oscillating field, and if the frequency of that field is right, transition between atomic levels can take place. In 1949, one of the co-laureates with Dr. Dehmelt, Norman Ramsey, modified this method by introducing two separate oscillatory fields. Due to the interaction between these fields, a very sharp interference pattern appears. This discovery made it possible to improve precision by several orders of magnitude, and this started the development toward high-precision spectroscopy. One important application of Ramsey's method is the Cesium Clock, an atomic clock on which our definition of time has been based since 1967. 1 second is no longer based on the rotation of the Earth or its movement around the Sun, but is instead defined as the time interval during which the cesium atom makes a certain number of oscillations. The cesium clock has a margin of error equivalent to 1,000th of a second in 300 years. The dream of the spectroscopist is to be able to study a single atom or ion under constant conditions for a long period of time. In recent years, this dream has to a large extent been realized. The basic tool here is the ion trap, which was introduced in the 1950s by another of Dr. Dehmelt's co-laureates, Wolfgang Paul and Bond. His technique was further refined by Dr. Dehmelt and his workers in Seattle into what is now known as ion trap spectroscopy. Dr. Dehmelt and his associates used this spectroscopy primarily for studying electrons, and in 1973 they succeeded for the first time in observing a single electron in an ion trap and in confining it there for weeks and months. One property of the electron, its magnetic moment, was measured to 12 digits, 11 of which have later been verified theoretically. This represents a most stringent test of the atomic theory known as quantum electrodynamics. In a similar way, Dr. Dehmelt and others were later able to trap and study a single ion, which represents a true landmark in the history of spectroscopy. This technique is now being used in development of improved atomic clocks, in particular at the National Institute for Standards and Technology, formerly the National Bureau of Standards, in Boulder, Colorado. Well, one of Dr. Dehmelt's students who worked on the ion trap at the University of Washington was Dr. David Wineland, and Dr. Wineland went on to win half of the 2012 Nobel Prize in Physics for his work. Here, Dr. Wineland, who works at the National Institutes of Standard and Technology in Boulder, attempts to explain ion trapping to simpletons like me.
We call them traps. So the simplest thing you can think of as analogy is like a marble in a bowl. The marbles are the atoms, they're charged atoms, and the bowls are configurations of, in our case, electric fields that allow us to grab onto this charge. The reason that's interesting is just that we can hold them for long periods of time, and we can do this without significantly perturbing their energy structure. Two aspects of the control is one is we'd like to manipulate the internal energy levels of the, in our case, the ions, the charged atoms, and that we've sort of known how to do for quite a long time using laser fields and microwave fields. But it turns out that we need to also control the motion of the atoms in the well precisely, and so we use a technique which is commonly called laser cooling. Freeze out the motion as much as possible within quantum mechanical limits. So at least what you can think about is this marble in the bowl, the harmonic oscillator. It has quantized energy levels, and with laser cooling, we can do a pretty good job of putting the motion in its ground state.
Here in a lecture, he describes some of the work that he did with Dr. Dehmelt in Seattle.
We were trying to get down to single electrons, and so in these experiments here, what we did is we drove this electronic circuit just to the point where the electrons in this trap were at such an energy that occasionally they'd gain through a collision process, for example, that they'd get enough energy to strike the electrode and therefore exit the trap. And you can figure in the marble analogy, it's just we're right at the edge where the marbles want to fall roll out of the top of the bowl. But anyway, we could get a picture like this. When we got down to this last step here, that indicated that we had one electron in the trap. And of course, this was part of the process in getting down to these small systems to be able to isolate single systems, in this case electrons. This was part of the work that led up to Dehmelt's Nobel Prize, where he performed a very accurate measurement of the electron's magnetic moment.
And finally, as we like to do, here is Dr. Dehmelt talking about what it felt like to win the Nobel Prize.
Things got going with my Nobel lecture on Friday. On Sunday, December the 10th, the day of the anniversary of the death of Alfred Nobel, the king awarded me my gold medal. Lectures at Uppsala, Göteborg, and at CERN in Sweden concluded the week. I felt for a week like a boy, or like the boy, who had to eat himself through a mountain of chocolate.
Well, there's a description we haven't heard before. I'm going to close on that note. I want to thank my producer and IT genius, Sid Tepps. What song to close with for Dr. Dehmelt? Well, since his work was related to that of one of his co-Nobel laureates, Norman Ramsey, and the Cesium Clock, I thought I'd close tonight with a song about time. And let's make it an enjoyable song about time. So as a final tribute to Dr. Hans-Georg Dehmelt, here is one of my favorite songs by the Association from 1968, Time for Living.